Hi, Matt Roscoe here at the University of Montana. This is a video lecture for our second week of the course, Math 595, Teaching Geometry from a Problem-Solving Perspective. It's a beautiful day in Missoula right now, and hope you're enjoying some beautiful weather too this summer. Let's get to it. So this week we're going to take some time to focus on content from a synthetic geometry standpoint. I think it's a good complement to our pedagogical conversation because the pedagogical conversation has to do with this idea of relationships, and that one of the aspects that we'd like to foster in our students when we teach them geometry is this ability to search for and prove relationships, which seems to be I guess one of the primary goals of a synthetic view of geometry. So let's talk about where we're going to go. So I'd like to review what synthetic geometry is. We introduced that the first week, but I'll put that definition up again this week. And then what I'd like to do is just give us a place to start by identifying some definitions and theorems that I think most of you will be familiar with. So that we can get someplace, I guess, in the lecture. And then I'd like to give you just two examples of synthetic geometry and how it can be applied to sort of a middle grades type of an activity. That would be example one, and then example two would be an upper grades or high school type of synthetic activity. So synthetic geometry, remember that this is sometimes called axiomatic or pure geometry. It's the study of shape using an axiomatic method that begins with a set of givens. Sometimes we call those axioms, or I prefer the word postulate because we're postulating that they're true. We're saying it's given. And it builds results. The results are usually called theorems. Sometimes we call them lemmas if it's a special case of a theorem. Using only the tools of logic and the tools that we use to draw points, lines, and circles. So that would be compass and straight edge constructions. Okay, a place to start. In traditional synthetic geometry courses, a class would start from basic assumptions, that would be your axioms or postulates, and build up new results using logic and constructions. But since we all teach geometry and have some familiarity with its basic results, I'm going to assume that you're aware of the following list of postulates, constructions, and definitions, as well as theorems. A proof card for each of these is available on our Moodle page, and I'll give you some links to resources for each of the results for those who want more information. So let's start out by talking about some known constructions and measures. So one thing we want to make sure we're all aware of is that 2 points define a line segment array. A complete rotation about a point measures 360 degrees. A straight angle measures 180 degrees. And then the definition of a circle, of course, as a collection of points that are equidistant from a center. So there's a proof card for each one of those, and you'll see me use those in a minute here. How about a few known postulates or theorems? So I want you to be, I guess, to be aware of the vertical angle theorem, the corresponding angles formed by parallel lines intersected by a transversal, that those are congruent, and four forms of triangle congruence: the side angle side, triangle congruence, side side side, angle angle side, triangle congruence, and then the isosceles base angles are congruent, and then the triangle angle sum theorem, which says that the interior angles of a triangle sum to 180 degrees. So hopefully you're familiar with these known postulates and theorems. It's a pretty small list. It would be kind of the list most commonly, I guess, addressed in middle school, and obviously developed and in high school as the results of geometry grow and are further, I guess, developed. So let's go ahead and get into it and do an example of engaging in synthetic geometry. So here's the first example I want to do. A rhombus is a quadrilateral with four sides of equal length. What geometric properties do the diagonals of a rhombus possess? So let's take some time to investigate this, to develop a conjecture. and then we'll try to prove it using the tools of synthetic geometry and the known postulates and definitions and theorems um, that we defined on the previous slides, and that are also defined on the proof cards available. So if I was asked this question, I'd probably first try to generate some information about it by taking a look at a rhombus's diagonals. We could do this by drawing, simple pictures of rhombuses, but it might be kind of fun to take some time to do some investigation in GeoGebra, and maybe I can give you a few tools that you might be able to use in your classrooms along the way. So I think this is a good opportunity for me to introduce the use of a slider. So I'm going to put a slider in here, and I'm going to call it length. How about side length? Or how about just, yeah, side. Let's try just side. Um, and we're going to run that slider from 0 to a maximum length of 10. And that's in centimeters originally in the canvas, the graphics pane, I guess, in GeoGebra. If you click on it, you'll see that it's about 20 high and maybe 40 wide in my picture view. But if you click on the grid, you could see that. So for example, if I click, if I click here, you can see that certainly 10 would be, if say this is the side length that I'm adjusting on the rhombus I'm intending to build, then 10 would be a nice maximum. Of course, we don't want a side length that's negative, so that's why I started with 0. Okay, so I'll undo the grid. I think it kind of clutters things. I also think it's a good size to adjust font size. If you're working in front of a class, I'd probably use a 20 font size, and that's under options and font size. So I'm going to build now a rhombus. So let's think about how we could build a rhombus. One way you could do a rhombus is you could start with a circle, right? But it might be nice if the circle was controlled by the side length of the rhombus. So I'm going to go ahead and get rid of the circle I drew. I'll click on each one of these and delete them. And I'm going to use, instead of circle with center through point, I'm going to use circle with center and radius, because if I choose a center and then type in a radius, it'll fix that radius. But in this case, I'm going to let the radius be controlled by the slider. So I'll just type in SIDE, which is the variable that's given to the number 4.1 right now. And what you'll notice then is that this will control the radius of the circle now. The slider actually controls the circle. If I put 2 points on the circle, then of course a line can connect 2 points, and since a circle is a collection of points that are equidistant from a center, then what do we have here? Well, we have basically one side of a rhombus, right? Because a rhombus has 4 sides that are of equal length. So far we have 2 sides of length 4.8 or 6.9 or 4. And what we like now is to find this next point, which is out here someplace, that also has a distance 4 from B and a distance 4 from C. So I'll use my circle with center tool again and type in radius side, hit OK. I'll use my center with radius again and type in distance side, hit OK, and put a point at the intersection there. Now we know that that point is both a distance 4 from C and a distance 4 from B. And if I connected that up with D and with C, then I think what we have now is we have a rhombus in there. It's kind of hard to see because of course the circles are in the way, but we can take the circles out of the way right like that, and of course grab the side, and now we have a rhombus that's adjustable in terms of its side length. It's also adjustable in terms of sort of where you can put B and where you can put C, because those of course are movable on the circle under which, if I kind of draw it up there or bring it back, the circle underneath the drawing, which B and C move along, allows them to be adjusted. So there we have a rhombus that is a rhombus, let's say by construction, meaning that it won't change from being a rhombus because the construction protocol restricts it to the circles that the points depend on. So I hope that's clear. Let's go ahead and fill in the polygon. It's always nice to have it shaded so you can see it nicely. So I'm using the polygon tool and filling it in. Maybe I'll make it a nice color like pink. And I'll pull these points out of the way. So what we're really interested in, though, are the diagonals of a rhombus. We want to generate some intuition about that. So I'll draw in these two diagonals. I think I'd like it if they were both a different color and easily identifiable. So I think I'll change their color maybe to blue and maybe make it I don't know, a dotted line since these are across the middle. And there we have it. We've got diagonals of a rhombus, and the rhombus is a dynamic rhombus, meaning that it can be adjusted to make any rhombus we want, as long as the side length is between 0 and 10, I guess. But you should take a minute now to sort of either play around with this on your own copy of GeoGebra, or just sort of watch me play with it and ask yourself, well, what seems to be true about the diagonals of a rhombus? What we're looking for is a relationship, right? If the figure is a rhombus, then what can we say about its diagonals, and what might always be true? I'll just take a little break here and let you think about that for a second as I play around with it. Okay, well, perhaps what you noticed was that the diagonals of a rhombus seem to be always perpendicular. This could be easily investigated on GeoGebra by just putting a point at the intersection of the two lines that are the diagonals and then measuring the angle. So let's just do that now. And it does appear that that angle is indeed 90. I'll move this out of the way so we can see. So alpha equal to 90 is what we're seeing in the angle. Sometimes I don't like the angles to carry their name and value. I'll just have the value in there. So I'm adjusting it to just 90 instead of alpha equal 90. And let's just see if that maintains 90 degrees. It appears that it maintains 90 degrees. Any place I move B and C, of course moving A won't do anything. But what if I scale the rhombus side length up? Of course those rhombuses seem to be all just similar. So it doesn't seem like there would be any change in side length. And scaling the rhombus up and down doesn't seem like there's any change in side length either. So there it is. It appears that rhombuses indeed do have side lengths which are, diagonals which meet at a 90-degree angle. Another conjecture you might make is that the diagonals appear to bisect one another. In other words, this distance ED appears to be the same as AE. So let's use the measurement tool and see if that's indeed the case. So I'm going to do distance here, A to E, and 7.08 is the distance from A to E. Let's see what E to D is. 7.08. Well, it does appear indeed that distance has been bisected. The distance B to E is 3.26, and the distance from E to C is 3.26 as well. Let's just see if we happen to get lucky with this particular rhombus, or if it's a universal property. If I move the rhombus around, of course the distances all move, but what I do notice is that regardless of where I move, these two distances remain the same and these two distances remain the same. So the rhombus itself does appear to have diagonals that are perpendicular to one another and they bisect one another. So I guess you could say the diagonals are mutual perpendicular bisectors. Let's go ahead and move to the proof stage now that we have a pretty good sense of what it means, what the conjecture is that we want to prove. I'll save this GeoGebra file and make it available on the website. Okay, let's move that off the screen. And let's get started here. So these are the proof cards that are available on the website if you want to copy them off and use them. I'll leave them kind of off to the side. And what I guess I'm doing is sort of, thinking aloud, using the cards as sort of a resource. Let's get started thinking about what it is we want to prove. So I'll do a paragraph proof, which is a verbal explanation in sentence form that explains why a hypothesis would be true. Let's write down the hypothesis. The hypothesis is this: the diagonals of a rhombus perpendicularly bisect one another. Let's see, proof. Well, let's draw a picture first. I'm going to draw the picture just exactly the same way that we did it on GeoGebra. I'll start with a center of a circle and a certain radius, put a couple points on that circle, and then keeping the radius the same, scribe out another another two arcs and drawing in their intersection. So we're getting a little bit of a compass and straight edge construction instruction here as well, how to draw a rhombus. There's our rhombus. Kind of erase some of this. And let's go ahead and draw in our rhombus. So I'll call this A, B, C, D. What should we call the point of intersection here? We'll call that E. Okay. So let's think a little bit about what we could do here. What we know right away is that these four sides, by definition of a rhombus, these four sides must be congruent. If those four sides are congruent, then we might be able to use some triangle congruence theorems, because I see lots of triangles that are possibly able to be, well, they sure look congruent. These four triangles, for example, look congruent, as does this large triangle and this large triangle. This triangle here looks congruent to this triangle here as well. So let's think a little bit about what we could do. If I move through to, how about this? These triangle congruence theorems. Then I think to myself, well, all I know right now is information about sides. I don't have any angles by definition of a rhombus that are congruent, so it seems like side angle side triangle congruence is going to be hard to establish, but side triangle congruence would certainly be all right. I do, though, notice that several of the triangles that I drew are isosceles triangles, and I do have one other piece of information there. We know that isosceles base angles are congruent, right? If I have an isosceles triangle, then these two base angles are congruent. So I could make a case for these two angles to be congruent and these two angles to be congruent because they're both members of isosceles triangles. And then, okay, so I could make some angle arguments. But ultimately, you know, it might be worth sort of thinking about, well, how are we going to get to our goal? I mean, what we want to show is we want to show that BE is congruent to ED, and that AE is congruent to EC, and that these four angles here in the middle are 90 degrees each. That would mean that the diagonals indeed do perpendicularly bisect. So how are we going to get there? I mean, the way I see us getting there, at least thinking about sort of the end goal, is I really want these four little triangles to be congruent. If those four triangles are congruent, well, then certainly this leg and this leg would be congruent because those would be corresponding parts of congruent triangles. And this leg would be congruent because they would be corresponding parts of these four congruent triangles. And then these four angles would all be congruent if all four triangles were congruent, which would mean if they were all congruent and they were, I guess, meet at a point, then their rotation, of course, about a point is 360 divided by 4 would give us 90 for each. Okay, so let's go ahead and that's our end goal. But in order to get this triangle congruent to that triangle, I need to know more than information about a single side. I probably need to know information about these two angles. Um, the reason I'm concentrating on these two angles is because what we're trying to show is about these two sides. So that should sort of probably pop out at the very end. We can't assume those two sides at this point are congruent, for example, to these two sides of this triangle. So I think the way to go would be to first draw attention to some of the side triangle congruences that we can do. So I'm going to first draw attention, I guess, to triangle ABD and CBD and try to make a case for their being congruent. And I can see that they are congruent because we have two sides here equal to two sides here and then a shared side here, which is of course congruent to itself. So that means that each of these two triangles on either half of the line BD are congruent. So let's make that case first. So let's see. Since ABCD is a rhombus, AB is equal to BC, AD is equal to, in length, CD, and of course BD is congruent to itself, so it's equal in length to itself. So we can say that, so triangle ABD must be congruent, ABD to CBD, by side triangle congruence. Okay, so what does that mean? Well, that means the corresponding angles must be congruent. So let's see. So if ABD is congruent to BDD, well, but the one thing we should notice is that, well, that means that the ABD, CBD, so the ones marked 1 and 1 here are going to be congruent, and the angles marked here, it would be 2 and 2 are congruent, right? But I think that we should probably be a little bit careful, because what we really want is we want both of those angles to be the same if we're going for triangle congruence on each of these four triangles. So, so we should also note that, so we've used side triangle congruence. But I think what I want to do is I want to use my isosceles base angles theorem, which says that anytime I have an isosceles triangle, the two base angles must be congruent. So that means the 1 and the 2 must be congruent. So I'll say also note that triangle ABD and triangle CBD are both isosceles triangles. So base angles are congruent. I'm going to just say combining these two results, justifies that angles marked 1, I'm going to angle marked 1, are all congruent and equal in measure. I don't know if I need to really say equal in measure, but I guess, so I can erase that now and say that, you know, these two are also should be marked 1. So that's two things going on there. The first thing is this triangle and this triangle are congruent. The second thing is that these base angles are congruent to each other. So that means these two base angles have to be congruent to each other as well. So all the angles marked 1 in this triangle and this triangle are equal in measure and congruent. So I can see now if I'm heading towards an end goal of trying to get congruence of these 4 triangles, I now have a side and an angle. And the question is where can I get one more piece of information to make some case. So if I have a side and an angle, I can see that for sure side, side, side triangle congruence is out on these. So what's left? It could be angle, side, angle, 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 side, or side, angle, side. I can see that I'm not going to be able to make a case for side, angle, side because I would have to know then that this side is congruent to this side, which would basically be assuming what we're trying to prove. So it's either angle, side, angle, or angle, angle, side that I need to use to get these 4 triangles congruent. And I can see right now that I could make a similar argument to the one that I just made to try to get these 2 angles congruent. And the way that I can do that is I can take a look at these long skinny triangles. I guess they're obtuse triangles, ABC and ADC, which are also isosceles triangles with congruent base angles and should be congruent one to the other by side, 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 right? Side, side, side. So that's what I'm going to do. I'm going to go ahead and say similarly, since ABCD is a rhombus, we can say that, let's see, AB is congruent to AD, so it's equal in measure, and BC is congruent to DC. I'm saying congruent or equal. I'm sort of being a little loose with that. Maybe I should be a little bit more careful here and call these congruent up here just to make sure my communication's on. Let's say these are congruent, even though they're equal in measure and congruence of a segment are interchangeable. And of course, I mean, what do I want to say there? Of course, AC is congruent to itself. I guess if I'm going to talk congruence, I should probably add segments over the top because segments are congruent, lengths are not. Lengths are listed without the line over the top. A segment, geometric object does have the line over the top. Okay, so similarly, since ABCD is a rhombus, we can say that these 2 sides are congruent, these sets of sides. And so I have 3 sides in correspondence with 3 sides of another triangle in correspondence. So what does that mean? So that means that triangle ABD must be congruent to triangle ABD. So ADC, let's see, by side, side, side triangle congruence. Okay. And they also are isosceles triangles, so I'll say the same thing here also. Note that triangle ABD and triangle ADC are, what are they? Isosceles triangles, and so have congruent, what did I call them? Base angles, or congruent angles opposite the congruent sides. So combining these 2 statements, we conclude that the angles marked 2 in the figure are congruent. I'm having a hard time with my lead this morning, sorry. So let's mark some angles too. So we've got this triangle congruent to this triangle, and these two angles congruent to each other. So the angles marked 2 here are congruent. They're corresponding parts in isosceles triangles. And at this point, I think we're ready to go for the jugular. Now we can see that we can make a case on all 4 of these smaller triangles for their congruency, and I'm pretty sure, well, I'm certainly sure that what we're going to use here is angle side angle triangle congruence. So an angle here and a side and an angle. If you read the card, what we have here are 2 sets of corresponding congruent angles. There they are, 2 sets. And 1 set of corresponding congruent sides that are between the corresponding congruent angles. And so we can make a claim for all 4 of those triangles to be congruent. Now we can claim, well, not even claim, we can state that. Let's do this in order, be careful. Let's see, so ABE, triangle, sorry you're watching me click my lead so much. ABE is going to be congruent. Let's see, ABE would be congruent to CBE, would be congruent to, let's see, CDE, and that would be congruent to triangle ADE. And that's by angle side angle triangle congruence. And so now we know that all 4 of these triangles, 1, 2, 3, 4, are congruent, so their corresponding parts have to be congruent. We get that for free once the triangles are congruent. And so, since the corresponding parts of these triangles are all congruent, we can state what? Well, we can state that, for example, BE must be congruent to DE, right? And what else? Let's see. I'm looking at the figure, so that means that one's bisected. AE must be congruent to EC. Is that true? Let's see. So it'd be AE must be congruent to CE. Yes, it is. So AE must be congruent to CE. So the lengths BE and DE are equal, and AE and CE are equal. This shows that diagonals bisect one another. I mean, that's really what we set out to prove, right? BE would have to be equal in length to ED, and AE equal in length to EC. So we've got the first part, but the second part is a little bit different, right? The second part is that these things perpendicularly bisect one another. To show perpendicular bisection, what do? We note that, well, I guess what we can note is we can note that these 4 angles here at the center are all congruent to one another. I mean, that's given here by the fact that all 4 of those triangles are congruent. So let's go ahead and make that case. We note from the first triangle it would be angle BEA has to be congruent to angle see BEA, so BEC has to be congruent to angle DEC, has to be congruent to angle DEA. So the measures of these four angles must be equal. Since we're going to use this fact, I guess I should get my proof card out just to make sure we're all on the same page. The sum of angles around a point, we think that the sum of angles around a point is 360. And these four angles certainly are around a point E. So I'll say since the sum of the measures of angles around a point must be 360 degrees. These four measures must sum to 360 degrees. That means they all must measure, just to make it completely clear to the reader, 360 divided by 4, 90 degrees. This shows that the diagonals are always perpendicular to one another. So I guess what we've shown is perpendicularity here. If I back up a step, we've shown bisection here. And so those were the two goals of our hypothesis. So let's just summarize. We have shown that diagonals bisect one another and meet at a perpendicular 90-degree angle as desired at the outset. And so that is the end of the proof. It's kind of interesting when you construct a proof to sort of go back and think about, well, what tools does the proof rely on? In this particular case, the tools that we used, the proof cards that we invoked were, let's just kind of highlight them. It might be kind of fun to think about it. So we used side-side-side triangle congruence. We used isosceles base angles, right? Isosceles base angles. And that was used twice, right? Side-side-side triangle congruence again. And isosceles base angles as well. And then that led us to a place where we could then use angle side angle triangle congruence. And from there, we were able to get the bisection out of the congruence statement. But then we also used measures of angles around a point. So the definition of a full rotation being 360. and that led to the perpendicular. So if we kind of go back and look at the prerequisites, sum of angles around the points, and let's see what else, and angle side angle, and side angle side, or side side side, and isosceles base angles. So definitely a situation where we needed some, quite a long proof, and we needed to use at least 4 different pieces of information that were previously proved or known. So it has quite a list, I guess, of prerequisites. Let's go ahead and stop there, and we'll make a second video for the second example, and we'll move on at that point.